All right, everybody, thank you for coming back for the last two talks of today. So for our next talk, we're very pleased to have Byung-Ha Hwang telling us about chromatic quasisymmetric functions and noncommutative P-symmetric functions. So let's get that started.
Okay. Okay, I'm really grateful to the organizer for giving me this opportunity. So in this talk, I will talk about chromatic quasisymmetric function and noncommutative P-symmetric functions. So before we begin, I want to mention two things. First, due to time limitation, unfortunately, I will skip graph theoretic interpretation for some definitions. So some notations in this talk differ from the notations in my abstract, but I guess that there is no confusion from this difference. So you can find more information about graph theoretic interpretation in the extended abstract. And second thing is, actually I'm not good at English, so I have tried to write my slide as detailed as possible. So if you have trouble in understanding my talk, please feel free to ask anytime. Okay, let me start. We'll start with the history of chromatic quasisymmetric function. In this talk, I will fix some positive integer n and let m be a weakly increasing sequence such that the entry mi lies between I and n. Then the natural interval order corresponding to this sequence is a poset on the n set with the relation given by I is less than p in the poset p if and only if mi is less than j. So this is an example. If P is the poset from 2, 4, 5, 5, 5, then its Hasse diagram is as follows. And we need to combat word combinatorics. So let P be a poset on the n set and W be the word on the same set. So type of the W is the represent how much times the letter I appears in the word. So we denote by W of mu the set of words of type mu. And I is P descent of W if Wi is less than Wi is greater than Wi plus 1 in the poset P, and we denote descent P descent of W, the set of descent of W. And there is another statistic, P inversion pair, well, blah, 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 but the important thing is there is a statistic which is very naturally defined on the word. So, okay. So in 1995, Stanley introduced chromatic symmetric function, which is a generalization of chromatic polynomials. But the original definition is not this, but we adapt this equation as the definition of chromatic symmetric function. So if for a given poset P, chromatic symmetric function is the sum of fundamental quasisymmetric function indexed by P descent of word, which is the word is of type 1 to the n. So there is a famous long-standing conjecture in algebraic combinatorics. For the natural interval of the P, the chromatic quasisymmetric function is H positive. This conjecture is still widely open. And after 2 decades, Scherzian and Waxis introduced the quasisymmetric generalized refinement of chromatic symmetric functions. So for a poset P, chromatic quasisymmetric function is defined to be sum of the fundamental quasisymmetric function with q weight, q to the inversion number. They proved that this quasisymmetric function is actually symmetric when P is natural unit interval order. So when we consider natural unit interval order, then this chromatic quasisymmetric function is sure positive. Additionally, Shershan and Wax's proposed a refined conjecture stating that the chromatic quasisymmetric function of natural unit interval order is also H positive. So, by definition, the chromatic symmetric function can be obtained by substituting q equals 1 into chromatic quasi-symmetric function. So, this implies that the refined conjecture proposed by Shershan and Wax implies the original Stanley-Sternberg conjecture. However, the P inversion statistic gives a clue for resolving the conjecture, which means by using the Q weight, we can group words based on their Q weight and focus only certain words rather than all of them. In addition, the chromatic quasi-symmetric function gives us a bridge between the chromatic symmetric functions and cohomology of Hessenberg variety. In this case, the Q grading on the word plays the role of the cohomology degree in the Hessenberg variety. So, this naturally leads us to the following question. Can we further refine the chromatic quasi-symmetric functions? And the answer is yes. I will explain how we achieve this refinement. Okay. So, now we fix a natural interval order P. We will deal with the slight generalization of the chromatic quasi-symmetric function. So for a non-negative integer sequence mu, here, defined multi-chromatic quasi-symmetric function is equal to the sum of fundamental quasi-symmetric function over word of type mu. So by definition, this generalization reduces to chromatic symmetric function and chromatic quasi-symmetric functions. So since the chromatic quasi-symmetric function can be regarded as a generating function of certain type word, so we introduce a refined version of the function by using an equivalence relation on words. So given a non-negative integer sequence mu, let gamma sub mu be a graph whose vertex set is W of mu, and two words W and V are adjacent if and only if W and V are of the following one of the following forms. The first case is that W and V are identical except for two consecutive letters, and the letters are comparable in the poset P. The second case is that W and V are identical except for three consecutive letters, and they satisfy these relations. So for two words, we say W and V are equivalent if they belong to the same connected component in this graph. So let's see an example. Let P be the poset from 2, 3, 3, and let mu be 1, 1, 2. Then W mu consists of 12 words like this, and we can find 6 edges of type. The first case, there is 6 edges, and we have another 4 edges in this case. So there is 4 connected components. And the following proposition play a key role in this work. This implies that the equivalence relation refines the chromatic quasi-symmetric function. So If two words are equivalent, then the P inversion statistic of two words are the same. But the converse is not true. So let gamma be a connected component of this graph, and we define case of gamma to be the sum of the fundamental quasisymmetric function where W belong to this connected component. Then, by definition, this function is just quasisymmetric function, but I proved that this is actually symmetric function. So we conclude that this slight generalization is also symmetric. So based on this refinement, I propose a stronger conjecture. So let's revisit the original one. The Stanley-Stanbridge conjecture states that omega x of p, chromatic symmetric function, is H positive. And second, Scherzer and Wax proposed that omega x of p, x and q is H positive. I further refined this conjecture. For each connected component gamma, case of gamma is H positive. This example illustrates the three conjectures and difference between them. So take P as the poset from 3344 and the mu equals to 1111. So there are 24 words of type mu, and we have the graph gamma sub mu. The Stanley-Stanbridge conjecture, the conjecture 1, says that the sum of fundamental quasisymmetric function of all words is H positive. And the second conjecture says that each summation of fundamental quasisymmetric function is H positive. So, and finally, conjecture 3 says that each connected component defines as H positive symmetric functions. So obviously, conjecture 3 implies conjecture 2 implies conjecture 1. Okay, and furthermore, the equivalence relations provide another advantage for studying chromatic quasisymmetric function. Since the relation focuses on the local property of words, so it leads us to the theory of noncommutative symmetric functions, which is powerful tool for studying such word combinatorics and proving several positivity. Okay, before we move on to the next part, I need to remark one thing. So natural unit interval order are characterized by 3+1 and 2+2 freeness. So the set of natural unit interval order is a proper subset of a set of 3+1 free poset. Originally, the Stanley-Stanbridge conjecture is about 3+1 free posets, although Guy Paquet showed that the positivity of all natural unit interval order implies the positivity of 3+1 free posets. I still believe that 3+1 freeness might be the key to resolving the conjecture. So I defined the equivalence relation for natural interval order, but it does not depend on the 2+2 freeness. So we can extend the equivalence relation and the refinement to 3+1 pre-poset. So in this direction, Blaszak, Eriksson, Piliavsky, and Siegel have some progress. Okay, now we'll move on to the next part. So consider the free Z module U generated by U1, Un. You can regard this ring, this algebra, as the polynomial ring with non-commuting variable. And we define I sub p to be the two-sided idea of U generated by this following element. Actually, these elements are just algebraic expression of the equivalence relations. So we introduce a symmetric function-like element in the algebra U. So first thing is the noncommutative P elementary symmetric function. We denote by E sub k of U, which is the summation of P decreasing sequence of monomial of P decreasing sequence. And for example, P equals the poset from 2, 4, 5, 5, 5, then E sub 2 is equal to U31 plus U41 plus U51 and U52. And there is no chain of rank 3, so E sub 3 is equal to 0. The second one is noncommutative P completely homogeneous symmetric function, which is defined by the summation of non-P decreasing sequence. And this theorem is called the commutation relation theorem, which plays a significant role in the theory of noncommutative symmetric functions. So, although the generator in U do not commute with each other, E sub k and E sub l they commute each other modular this idea. Thanks to this theorem, we can define other noncommutative symmetric function by using relation between usual original symmetric functions. So recall the Cauchy product, and we can define noncommutative P Cauchy product. Omega sub xu is equal to the product of the summation x sub j to the L times h sub L of u. It is very easy to see that this noncommutative P Cauchy product can be written as follows. So the summation of fundamental quasisymmetric function times the u sub w, where the w ranges over all words. And u star be the free G module generated by the all words W, and Q star is the just scalar extension of U star. And define bilinear pairing between U and U star like this. Pairing of U sub W and V is equal to chromatic delta of W and V. Finally, we define small gamma sub gamma is the formal sum of the words belonging to this connected component, and gamma sub mu is equal to the formal sum of word of type mu with their q weight. Then by definition, we recall this expression, and this pairing, we have the k sub gamma is equal to pairing of omega and small gamma of gamma, and chromatic quasisymmetric function is pairing of omega and gamma mu. So this is the strategy for proving positivity. So suppose that noncommutative P Cauchy product can be written as follows, which is the summation of a symmetric function basis g lambda x times certain noncommutative symmetric function f sub lambda. Then when we extend this this k sub gamma extend g expansion of k sub lambda, k sub gamma, and g expansion of chromatic quasisymmetric function, then we obtain this coefficient by pairing of noncommutative symmetric function and the gamma of gamma, gamma sub gamma, and gamma sub mu. So if H sub F sub lambda has a positive monomial expression modular I sub P, then K sub gamma and chromatic quasisymmetric function are also G positive. Okay, in this manner, we can prove some positivity of two symmetric functions. So, but I have no enough time to. So we can write the noncommutative P sure function as the summation of the P tableaus. So we can find like this expression from as very combinatorially. So and we can define noncommutative P monomial symmetric function and have this expression. So finding a positive monomial expression of this function is equivalent to the finding of positive combinatorial interpretation of coefficient of H expansion of K of gamma, which prove conjecture 3. So I have a partial progress. So when lambda is of hook shape or two-column shape, the noncommutative P monomial symmetric function has a positive monomial expression. So the K sub gamma is H positive when lambda is of hook shape or two-column shapes. There is further direction, but I should stop here. So there is a reference, and okay, thank you.
We should have time for a few questions.
Yeah, so can you, if you go back, the very last slide you said, no, the one before that, sorry. So you said you proved this in the special case of those shapes. What is the coset T for this theorem? Is it any 3 plus 1 avoiding coset, or is it any interval coset, or is it just any coset?
Oh yeah, the question is there is a restriction on this result on the poset P. In this case, I proved for every natural unit interval order poset. Every natural unit interval order.
Do you know if the general, just more not just with this special case for lambda, but do you know if do you think the conjecture is true for the more generally 3 plus 1 avoiding, or do you have any counterexamples?
The question is this theorem can be extended to 3 plus 1 pre-4 set. Am I right?
Or not just this one, but just conjecture 3 in general.
Conjecture 3 in this direction, I just said. Okay. In these 4 papers, have some progress for 3 plus 1 pre-4 sets. So.
Yeah, but do you think the 3 plus 1 pre is a condition that you would need? It won't be more general than that, do you think, or do you think it could be used for any poset?
Oh no, I don't think this is hold for any poset P.
Okay.
Yeah.
Thank you for the interesting talk. Just have a question here. You mentioned that you think that it's key to go to 3 plus 1 free. Also for the refinement, can you say more, since maybe it's not quasisymmetric once you leave the unit interval order? Just if you can say more why you think we should look at the bigger family.
Sorry, I don't understand.
So you mentioned here that one should look at the bigger family.
Yes.
To attack the conjecture and also for the refinement. But what happens when you don't have something that's symmetric, but quasisymmetric? How does that work?
Oh.
Sorry, you mentioned that you think we should look at the bigger family. Can you say a bit more why?
The question is what? Also, I don't understand. I don't fully understand your question, but the reason why I consider the only natural interval orders, not the 3+1 preposet, is actually I use the model of the unit interval. There is a geometric diagrammatic model for this natural unit interval orders, and my work depends on that models, but 3+1 preposet does not have such model. So, but I think this equivalence relation on words can be extended to 3+1 preposet. So, and now this I certainly I'm sure that this conjecture 3 is true for 3+1 preposets.
All right.
For your practical result, how difficult do you think it's going to be to extend the shape from 2 columns to just make a rectangular shape?
As far as I know, the rectangular shape also proved by Siegel or Erickson. So, but other case, not hook shape, not 2 column, or not rectangular, the other shape, I think, very difficult to resolve this conjecture.